Okay, welcome back. We're going to part two of the life cycle of stars. In the previous presentation, we talked about main sequence stars fusing their hydrogen into helium. And I think we talked very briefly about what's going to happen when you're all helium in the core or you're mostly helium. Two things happen simultaneously that are kind of in opposite directions. The inner helium core collapses again under gravity since there's no more fusion heat to push outwards and hold the star upwards. Meanwhile, as that helium core collapses, it heats up again for the same reason that originally the star heats up as you compress things. So that gravitational energy gets turned to thermal energy and eventually heats up even hotter, and you start fusing the helium into carbon, which I'll talk about in a second. That heat then causes the outer layers of the star that didn't undergo the gravitational collapse to be pushed outwards and become huge, and that becomes a red giant, right? And as it expands, it cools, and those outer layers will, for a star our size, will come out past our own orbit. Um, and so even though it is not as bright, it is so large that these are not hard to spot because they're so big. What's going on in the core, though, is kind of interesting. Why doesn't helium just fuse with helium and make element number 4? Well, it does, but it's an unstable isotope of beryllium, so it will not hang around. However, while that unstable beryllium is there before it has time to fizz apart, if it gets hit by a third helium nuclei, that can fuse, and that can give you element number 6, and that is the stable isotope of carbon. In fact, this is where the carbon in your body came from, right? All the carbon in the universe was created in this triple alpha process, right? In the Big Bang, when we look at the oldest stars in the universe, there is no element higher than number 3. And so we're fairly confident that all the carbon and all the life forms on Earth were created in a white dwarf, in a triple alpha process in a star that lived and died before our sun ever came to be. Now, the red giant swells up really big. We've already kind of talked about this. This white dwarf now, after that triple alpha process happens very quickly, but it's super hot, right? So it's glowing white for millions of years, and it would be very slow to cool off because it's all densely packed in there, right? It's hard to radiate all that energy out. And what's holding it up now is just there's all these carbon atoms. It's a big lump of coal basically out there in outer space, and if the remaining mass is less than 1.5 times the current mass of our sun, then the gravity will get balanced out by that electrostatic repulsion, right? The protons and the loose electrons hanging out in there will hold it together, and that'll be a stable configuration till the end of time, as far as we know. Now, as that white dwarf radiates its energy, eventually, it will no longer glow when it's not hot anymore, and theoretically, the carbon would still be there. It would just be cold, and so that would become a theoretical object called a black dwarf, right? So, as far as we know, the universe is not old enough for any white dwarfs to have cooled down to that status, so we don't expect to find any. Of course, they would be hard to find since they're not giving off any thermal signature anymore. Now, what happens to larger stars? So, stars that would end the triple alpha process at larger than 1.5 times the solar mass, right? There's a little bit of confusion when you start comparing the sizes and masses of stars on their life trajectory, because there's the beginning point before they fuse their hydrogen into helium, and then there's their how much mass is left at the end, right? So that's why you'll frequently find different numbers that vary quite widely. But if the remainder of the star at this point is larger than 1.5 times the current mass of the sun, right, which is a really tightly packed object. If you think about it, you're talking about something that has more than 1.5 times the mass of the sun packed into something the size of the planet Earth. So that's ridiculously gravitationally intense. If there is more mass than that, then gravity will win out over the proton-proton repulsion and electron-electron repulsion. In other words, that electrostatic force will not be enough to hold the star up, and so it will collapse even further. And of course, as it collapses, it will heat up again, and we start triggering fusion of the higher elements, that is, elements above number 6 for carbon. And what happens is, as you go deeper and deeper, you get this onion peel effect where the temperature rises, and so you're able to fuse heavier and heavier atomic nuclei, right? Because the more protons you have, the more thermodynamic energy you need to give those nuclei so that they'll actually get close enough for the strong nuclear force to reach out and grab and fuse them together. And so this process will continue until the inner core, which is the hottest part, eventually will be fusing into element number 26, right, which is iron. So notice that this is primarily even numbered elements, right, because you're starting this process with carbon and helium mostly, and most of the hydrogen has already been fused or expelled or is in the outer layer, right, and this is the explanation for why certain elements appear in the abundance chart to be much higher than other elements in the universe. It's because of this specific process, right? Just like I was talking about with carbon, every element heavier than carbon is created in these high mass stars. Now, element number 26, iron, is the end of the line, right? And if you look at the atomic abundance in the universe, there's a precipitous drop-off past iron. Now, why is it that's the end of the line? It's because what nature is doing is they're squeezing energy out of these nuclei by fusing lighter elements, right? What's going on is gravity will squeeze in, and some of that gravitational energy will get, will be transferred into these stronger nuclear bonds, which then releases energy. And so the process is like a familiar one, right? That we were talking about from the beginning with hydrogen going into helium. But in element number 26, once you get past sticking 26 protons in there, it's no longer an energetically favorable thing. You're no longer going downhill on the energy thing. You're not going to release any energy by adding more protons to a nuclei of iron, right? In fact, you're creating slightly more unstable elements, right? You're making the elements on the periodic table that actually would undergo breaking apart, that is fission, in order to release their energy, right? So here's a chart of binding energy per nucleon, right? And you can see all this enormous amount of energy you're releasing as you fuse higher and higher. And then iron is the inflection point, and after that, you've got these really large unwieldy nuclei that are going to release energy by fizzing apart, right? So that's the turning point for what elements are appropriate to give you energy from fission and what elements are appropriate to give you from fusion. So nature has a big problem here when they hit this stage and they've fused iron. There's no more, if gravity is pulling in and there's no more way to release any energy by fusing nuclei, you're going to have to turn to a different process, right? So what happens at this point is gravity is going to pull in, and yet the nuclei will not form heavier nuclei. And so there's one option left, which is you can actually pull the electrons into the protons, right? Because they're oppositely attracted. And when you do that, that's reverse beta decay. You are creating a neutron. And so what happens in this final stage when you've got an iron core, and this happens extremely quickly, is there's a gravitational collapse of the electrons into the protons, and now everything in the core of that sun becomes 100% neutrons, right? And you have the creation of a neutron star. When that happens, it's a cataclysmic explosion of energy, right? This is a ring, an expanding ring of an energetic wave that is being emitted from that collapse that happened in a very high mass star in the middle, and that explosion is called a supernova, right? And so these supernova are just incredibly energetic events, right? You've got this, the collapses happens in a matter of seconds from that iron core, and there's an enormous amount of energy, and all of these heavy ions that were created in that onion layer of fusion are being spewed out, right, along with this explosion of energy. And it is that combination of relatively heavy nuclei and a bunch of excess energy that creates all of the elements higher than number 26 on the periodic table, right? So anytime you find an element on planet Earth that has an atomic mass, atomic number bigger than 26, you are finding the remnants of a supernova decay, right? Here's a picture, I think taken by Hubble. This is several images on top of each other, right? So one's like taken in infrared and stuff, but this is like the remnants of a supernova explosion. And so it's emitting lights in all kinds of spectrum because it's actually kind of littered with all these different sort of nuclei and is elementally very varied compared to the rest of the universe, right? So this is where it is thought that all of our interesting mix of elements here on planet Earth came from, is the dust cloud that the solar system collapsed from was near a high mass star that went supernova before the dust cloud even collapsed, and it spewed all those heavier elements into our dust cloud and enabled all these hard rocky planets to form and all of this kind of varied chemistry to exist on planet Earth. And that's why we can dig into the ground and dig up these radioactive isotopes and all these other things that date from more than 4 billion years ago. Here's an example of a telescope that has captured a supernova event, and then where there was a star, there's a white dot, and that, of course, is a neutron star. So these neutron stars, it's like the white dwarf on steroids, right? It's not just one big solid mass of wall-to-wall carbon. It's incredibly dense. This is the densest accessible material in the universe. It is like one giant nucleus, right? It is 100% neutron, so there's no empty space at all. You know how atoms and matter is all mostly empty space, and that's because the electrons take up a lot of room. Well, there are no electrons left in the neutron star, right? There's no charge at all. It's just solid neutrons, right? And so you get these kind of ridiculous kind of things about just how dense it is, you know, what a teaspoon would weigh and all that kind of stuff. It's basically you've got 1.5 solar masses left, typically, after the supernova explosion, and it's packed into something the size of Chicago, right? So that's unimaginably dense, right? Now, what's holding it up at this point is basically the Pauli exclusion principle, right? The fact that you can't have fundamental particles having the same quantum address. And at this point, if what's left in the neutron star is less than 3 times the current mass of the sun, that will be a stable configuration, right? And just like the white dwarf, these neutron stars will radiate their heat for eternity, basically, until they cool down also. But they'll just sit there as a big mass of neutrons. Now, if it's larger, well, before I go to what happens larger, because there's one more step to all of the story, the study of neutron stars is kind of an interesting kind of thing where it's like you're bringing astrophysics, looking at big things far away, in contact with people who try to understand the composition of the nucleus of individual atoms here on Earth, right? And so this neutron star is something that people do a lot of models on, and they try to get some data. And there's active research in like what are the dynamics of something that's 100% neutrons like that? How do you think about it? And a lot of the models actually model it, and this is true for a lot of atomic nuclei too. It's modeled more like a liquid than a solid. There's a special subcategory of neutron stars that when they were discovered in the 60s, it was super exciting because people thought they'd actually found radio transmissions from aliens. And what happens, what it was found to be was a lot less glamorous, but still very interesting from a scientific point of view, is that some of these neutron stars, as they're collapsing, they keep the magnetic fields of their mother star intact. And so the whole ice skater conservation of angular momentum thing is still going on. And so as the star collapses into a neutron star, it's spinning at an extremely high rate now to conserve angular momentum because it's so small. And if the magnetic fields are preserved, they act like giant egg beaters in space, right? And so you've got this magnetic field that's whipping around, that's following the neutron star as it rotates around. And and of course, because of the collapse, the area is going to be littered with a lot of charged particles, and those magnetic fields will pick up these charged particles and accelerate them. And of course, those accelerating charged particles will create electromagnetic radiation, right? And so what they heard was like a radio signal that had a beat frequency, and it sounded artificial, right? It was like 1 beat every 3 seconds or something like that. And they're like, at the time, they couldn't think of any natural phenomenon that would create this. And then they did figure out that it would be possible, and that, of course, is, and that's where they got their name, the pulsing. It comes from the noise that they create due to their rotation. So here's an artist's rendition of the magnetic field lines around a pulsar as it rotates. Now, if at this point, not at this point, but if the mother star, when it collapsed due to the supernova explosion, would have had more than 3 solar masses left, the quantum degeneracy of wall-to-wall neutrons is actually not enough. So gravity can do one final thing, and that is say, I am so powerful, I'm going to actually collapse all you neutrons anymore. You're going to lose your identity as a subatomic particle, and I'm going to collapse this mass into a singularity. Now, how to visualize that or what that looks like, I think is kind of beyond the scope of what people can do. I mean, people can model these things mathematically, but like what it actually is going on in there in the heart of a black hole, we don't know. But this is the creation of a black hole, right? So the largest stars, when they die, they will end their lives in a black hole. So the supernova explosion will clear and you will see nothing, right? Because the idea of a black hole is the gravitational field has become so strong, right? This is a ring that would be quite some distance away from the singularity where all the masses collapsed. And the size of that radius, of course, is dependent upon the mass that's inside the black hole, with a larger mass creating a larger singularity, which creates a larger, what is called an event horizon, which is this radius around it. It's this sphere of blackness. And why is it black? Is because the warping of space-time is so severe that even light cannot get out. And so light falls in there and never comes out. And that's the lack of all color. It's what we call black, right? So here are the three end states for stars, right? The lightweight guys like our own sun will end their life gravitationally being pulled in, but then held outwards by the electrons and the protons, just regular electrostatic forces that kind of hold matter up in our everyday life will hold that white dwarf up. However, if the gravity is strong enough, it will collapse all of those electrons into their protons, and you'll get neutron stars. And the quantum degeneracy of the neutrons, the Pauli exclusion principle, will hold that neutron star up. However, if the star was even larger, and the remaining mass, as this graphic shows, larger than 3 current solar masses, and this is, of course, after all these different fusion processes have happened. Its main sequence, hydrogen fusing into helium, the triple alpha process going into carbon, the onion layer peeling of medium and high mass stars, making all those elements through number 26, that supernova explosion that sends all that energy and mass into space. If what is left at that point is greater than 3 solar masses, then a black hole can be formed. So black holes are a subject in and of itself. I think I'll do another presentation on them, but those are the basics for now. And a crazy kind of idea. The idea of black holes was proven to be consistent with general relativity just a few years after Einstein published his paper. But of course, the first one was not observed until the 1960s. And when it was observed, it was not observed directly. It was observed by a companion star orbiting around it. Since then, we've made many positive identifications of a black hole. And within the last 2 or 3 years, have actually visualized one in a video that I'll share with you a little bit later. But here's a good chart that kind of summarizes the whole thing, right? So if you start on the left and have a timeline moving to the right, you've got some nebula of gas. There's no structure in it, but the gravity of the mass in that nebulous cloud collapses it. You get a main sequence star where hydrogen is fusing into helium with the proton-proton fusion. The lowest mass stars like our sun will follow this bottom trajectory when they get to the end of their lives, where you get this red giant that gets pushed out by the triple alpha process in the middle. The outer layers peel off and disintegrate in something called a planetary nebula. And then the inner core where the helium is fused into carbon will be revealed, and we'll see a white dwarf in there, which will cool off. As it cools, it will go through the spectrum down to red, and then eventually end as a black dwarf, emitting no more radiation as it's cold. The heavier stars have 2 pathways. They'll all do this onion layer peel thing until they get to element number 26, which will then, when they try to pull in on the iron, the nuclei will refuse, and you'll get a rebound effect, and then you get the electrons being pulled into the protons, and you get this supernova explosion, creates all the heavier elements, all the radioactive isotopes on Earth and all that kind of stuff were created in supernova explosions before. And then you have 2 endpoints depending on their masses. At that point, the heaviest stars forming a singularity in the fabric of space-time known as a black hole, and the medium weight ones, I guess we'll say, end their lives as a neutron star. Okay, so there you have the life cycle of all the stars in one graphic. All right, that's a good point to end for now.